Hello class, it's Mr. Cablan again, and I'm here to present lesson number 4 in chapter 5, dealing with slope as a measure of rate of change. So before I begin today's lesson, I just want to do a quick recap of what we've covered so far here. So if you take a look at the screen here, what I have on the screen here are all the formulas that we've seen up until this point. So from the first lesson, we learned direct variation, and every equation of direct variation is y equals kx. And when we have partial variation, okay, the equation for that is y equals mx plus b. Now remember, graphically, the only difference between these two is that direct variation have graphs starting at 0, 0, and partial variation have graphs that start or pass through anywhere else. All right, and the b represented what was called the initial value, and later on you'll see this to be what's called the y-intercept. Now, from the last lesson, okay, you learned the first calculation of slope, okay, and remember that slope is represented by the letter m here. So the letter m here represents slope, and right now you have learned to calculate slope using one formula, which is rise over run. So remember in the last lesson that anytime you have a line that's falling down to the right or going up to the right, you have to draw what's called a rate triangle, and then you just count the number of spaces that are going up and down for the rise, and how many spaces are going from left to right for the run, and that's how you calculate the slope of a line. Now, slope for the remainder of the course will always be designated by the letter M here. And the reason why I'm bringing that up today, and we're going to revisit this screen at the end of today's lesson, because this is the screen we're going to use to summarize all the formulas that you will need to know for this particular chapter. In today's lesson, you're actually going to learn another formula for the calculation of a slope, and then we're going to go over the times you can use certain formulas for certain types of questions. All right, so let's get right to it over here, and let's take a look at slope again. But this time we're going to look at it and then basically use how we can apply this to problems dealing with rate of change. Now, you keep hearing this word rate here because we've seen it many times already in this course here, and it's no different in this particular example. In fact, one of the examples, we're actually going to tie in what we did in the review as well as in the last chapter, and then relate it back to the calculation of slope using rise over run. So when we're looking at slope, okay, slope is now a formal calculation of the rate or the rate of change. So when you're looking at a graph, for example, okay, and anytime you see a graph, the most common approach to calculate slope is to use rise over run. Okay, and basically what a rate of change is basically a change of one quantity over the change of another. And remember when we were doing the grade 8 review, anytime you have rate, you always have 2 units. So it's going to be 1 unit over another one. So this is actually going to be revisiting that as well. All right, and as I mentioned before, when we're looking at rate of change, there's always going to have 2 units, and the most common unit that your people are familiar with is something like kilometers per hour, which is the unit for speed. All right, and again, the purpose of the slope, again, is just a formal calculation of the rate of change for any type of scenario that you have. And our brand new formula, okay, this is very brand new for you, is given to you on the screen. As you can see, I put a box around it. And the formula we're going to use for that is y2 minus y1 over x2 minus x1. Now, you're probably wondering, what in the world are all those letters and all those numbers? Well, anytime you are given a graph, or you're given a scenario where you don't have a graph, or if you have numbers that go up by a different amount, okay, you're going to see this is going to be the most commonly used formula in order for you to calculate slope. And in fact, you can use this calculation for slope for any type of problem involving slope or rate of change. Now, looking at this graph over here, when you're labeling points, okay, always label them consistently in the way that I'm about to show you. So you notice what we have here are 2 points. Our first point here is 1 and 2, okay, and our second point here is 6 and 5. Okay, when you're labeling the points over here, always label them in the following manner. You're going to label the first point here as x1 and y1. Now you're probably scratching your head, what in the world is x1 and y1? Well, you know that each ordered pair or each coordinate consists of two numbers. The first one being the x, the second one being the y. These little tiny ones, the bottom right hand corner, are simply just reminding us that this is the coordinates, the x, y coordinates of the first point. So if this is x1, y1, that would only make the second point here is x2, y2. Now, the general rule of thumb when you're labeling points, always label the points from left to right. Okay, and whatever you do, do not mix and match the letters with the little tiny numbers. Like for example, do not put down, for example, x1, x2. Don't put in x1, y2, etc. First point is always x1, y1, and second point is always x2, y2. And you're going to see we're going to be using this formula for the remainder of the chapter, especially when we get with start taking a look at numbers, bigger numbers, and scenarios where we can't count the number of boxes on a graph. All right, so that's the brand new formula for this chapter, which we're going to see towards the end of this lesson. So just keep that in mind when we get to that particular example. So the first example we're going to deal with, I know right now it's hard for us to be connected to this sport because there's no sports going on at the moment over here. So right now we're going to be looking at the speed of a hockey player. So what we have here is that we have a hockey player skated 60 meters in 5 seconds. Okay, and so another way to interpret that is that in 5 seconds, this hockey player was able to cover a distance of 60 meters there. All right, so first calculation we're going to do here is we're going to calculate the rate of change of the hockey player. And we're going to do this the exact same manner that we did back at the beginning of this course. And all we're going to do for this is take the distance of 60 meters, okay, and then divide it by the time of 5 seconds, just like we did in the beginning of this course here. Now, you notice that what I've done here, I've included the units in the calculation just as a reminder that our final answer will always consist of 2 units. Because remember that rate is always a change of one unit over another. Now, when we divide these two numbers into each other, that's going to give us 12. Okay, but remember the units will consist of 2 units. In this case here, it'll be meters per second. Okay, and the way we explain that in words is the fact that this particular player, he covered 60 meters in 5 seconds, and as a rate, okay, it's going to be 12 meters per second, or 12 meters for every 1 second there. So again, this is just a quick review of what we did in the first part of the course here. All right. Now I want you just to make a mental note of this number because we're just going to do some comparison towards the end of this example. Now, what we're going to do with this is now we're going to graph it. And believe it or not, the only piece of information we have right now is what we have in this single question here. So it says here, graph the hockey player's distance with respect to time. So when we're looking at a graph over here, when you're labeling, okay, remember going back to independent and dependent variable, okay, you have to ask yourself, does the distance in meters affect or control the time, or does the time control the distance? Well, we should know that it doesn't matter if the hockey player is traveling or not. It will never, ever control the time because time only moves in one direction. So in this case over here, the independent variable or the variable that's in control, that will be the time. So that goes on the horizontal axis. So that would make the distance in meters be on the vertical axis. All right, now, when we're plotting this particular point, let's just think about this for a second. Let's think about a hockey player or any sport for that matter. Okay, so before you actually skate, guess what you're doing? Okay, you're stopping. So at rest, okay, you're not moving, therefore you're not covering any distance. So your first point is actually going to be the point 0, 0. All right, so from here, all we're going to do here is connect this point of 5 seconds and 60 meters. So I went right 5 and up 60, and I'm just going to connect it to the point 0, 0. All right, now think about this, okay? What type of variation do we have? Jeopardy theme. Ding, 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 ding. Yep, you guessed it. This is an example of what's called direct variation because we have a line that starts at the point 0, 0. All right, so that's the graph that we have in this. So it says, explain what rate of change means in this example and how does it relate to the graph. So what we're going to do for this one is we know the fact that when you're taking a distance and you're dividing it by the time, that gives the speed of the player. So we know that the player skated 60 meters in 5 seconds, and the word explanation for this is that when we convert that and express it as a rate, we know that he expressed it as 12 meters for every 1 second. And the rate of change, again, in this case, is the slope of the line. Now, what I'm going to show you for this example is just another way to calculate slope, but also keep in mind what we have here in the graph is something a little bit different than what we're accustomed to seeing. So What we're going to do here for the slope of the line is use our rise over run, but I want you to pay very close attention in terms of how we're going to do this. When we're drawing the rate triangle, we only have 2 points to work with. We have 0, 0, and we have this 1 point over here, which is which is 560. So I'm just going to draw a rate triangle just like that. Now, take a moment. I want you to take a look at the horizontal axis, okay? And I want you to take a look at the numbers. Notice the numbers on the horizontal axis is that every other box is going up by 1. All right, keep that in mind. If you take a look at the vertical axis, you notice that these numbers here are going up by 5. So we have a slight problem that we have in this question over here. Now, the reason why we drew that big rate triangle is because when you're doing rise over run for this particular type of question, okay, we actually need to refer to these numbers that you see on your graph. So starting off with the rise over here, okay, instead of counting the number of boxes, okay, what I want you to take a look at is the value of the rise based on what you see on the vertical axis. So if you look at this dotted line over here, okay, and you measure it, okay, notice what we have here would be a rise here of 60, all right? So the reason why it's 60 because the distance between the bottom here all the way to the top of this point is 60, and we're just reading it off these numbers over here. Same thing with the bottom part. Okay, notice that every other box is going up by 1. But however, in order for us to use the run for this one, we're just going to use the numbers that we have here. So you notice from the bottom left all the way to the end of the rate triangle, the run here would be 5. All right. Now you're probably wondering, um, do we have to do it using rise over run for these type of questions? And the answer to that is no. And you'll see that in the last example, that this is probably not the best way to approach it. But for the time being, I just want you to see that when you're using rise over run in a graph and the numbers are not going up by 1, that this is an alternate way to do it. Now, when I put the numbers in over here for rise of 60 and a run of 5, okay, whoa, this looks familiar, doesn't it? Well, it should because it's the exact same calculation that we did in the very first example when I asked you to calculate the rate of the particular hockey player here. So 60 over 5, again, you notice it's 12 meters per second. So you notice we did 2 different questions and we got the same answer for both of them. So this is telling us right now, or helping us understand, that when you're calculating rate, it's the exact same thing as the calculation of the slope of a line. And that's exactly the connection between slope and rate of change. All right, so what we're going to do now is we're going to take it up a notch and make things a little bit more difficult over here. So if you thought the last example was a little bit challenging, this one over here, okay, is going to be brand new because we're now going to do something a little bit different than what we've been accustomed to seeing. So when we're calculating the slope of the line, up until now, we've been using rise over run. Now, for this particular question, okay, it's probably not the best approach to it because if you take a look at the numbers over here, okay, if you take a look at the horizontal distance, which represents the altitude or the height in meters, okay, you notice that every other box is going up at 2,000, okay? So rise over run probably is going to be very, very difficult for this. Same thing with the air pressure over here, okay? Notice the air pressure, okay, every other box is going up by 200. So rise over run, again, probably not the best way to do this. So how in the world are we going to solve this problem if we're not using rise over run? Well, the way we're going to do calculate the slope of this particular line is we're going to use our special formula, which I introduced you on the first slide. Now, before we do that, take a moment and I want you to take a look at the line because we just want to make a little bit of a prediction before we actually start doing the math behind this. Notice what we have here, okay, is a line that's falling down to the right. Now remember that any line that falls down to the right will always have a negative slope. So our final answer has to be a negative. All right. Now, step number 1 for this one, since we're calculating the slope of this line, okay, and we're going to use, it's the first time we're going to use this, okay, we're going to use our special formula of y2 minus y1 all over x2 minus x1. Now, again, you do need to memorize this formula. So again, please make sure you commit it to memory. Just write it over and over again. And make sure you also remember that the top part is the y2 minus y1, and the bottom part is the x2 minus x1. Now, just as I said in the first slide over here, when you're labeling the points, always label the points from left to right. So if you take a look at 0 and 1000, I'm just going to write that down as x1 and y1. Okay. And as I just said before, whatever you do, do not change that. And it's x and x1, y1, because remember that coordinates are always expressed in x and y. And these little tiny ones remind me that it's just the first point. Okay, so that's x1, y1, and second point is x2, y2. Now, it is very important that you're labeling the points accordingly because it helps you see where the numbers need to go in this fancy formula over here, all right? So if you take a look at y2 minus y1, what we have there will be 500 minus 1,000, okay? And then for x2 minus x1, we have 6,000 minus 0. Now, take a moment before we do that as you're writing this down here. If you remember, I just did this as a quick mental note that any line that's going down to the right is always going to be negative. So you can see that once we put these numbers in and simplify it, okay, guess what? Notice we already have our negative slope there, all right? And don't forget, always express your fraction in lowest terms, and we get there a final fraction there of -1 over 12. Okay, so just to recap what we did, okay, we use our fancy formula. I just refer to it as that. Okay, we use these for scenarios like this, where the numbers are not going up by 1, and when you're looking at questions like this, okay, notice the numbers are also very, very big. Okay, so when in doubt, use this formula. In fact, you can use this formula for any type of question dealing with slope, as I mentioned earlier. Okay, so feel free to use it for every type of question. All right, so next thing we want to do here is just to talk about what slope means in this particular question. And this is going to be a little bit difficult to understand at first because it's not really something that you're familiar with. But basically what this question deals with is that when you're climbing up a mountain, okay, the air pressure decreases. Okay, and that's why people who go up in the mountains, they tend to have a hard time breathing. That's exactly what's happening over here. And basically what's happening over here is that as the height or altitude increases, the air pressure decreases. Okay, so this is again connecting this to independent and dependent variables and how one affects the other. All right, and in this case here, if we were talking about the number itself, and this is again something you just need to wrap your head around at first, is that means that the air pressure will be decreasing 1 millibar for every 12 kilometers of altitude. Okay, so that's just a verbal explanation for this particular question. All right, so again, just to do a quick recap over here, again, I introduced you to this brand new slope formula. Okay, don't forget, always label the first point as x1, y1, and the second point is x2, y2. All right, once you have that, plug it into the formula, and don't forget, always express your slope as a fraction in lowest terms, or if it's a whole number, express it as a whole number. All right, so that wraps up the lesson here. So I'm just gonna go back to our fancy formula sheet over here. So if you take a look at this, like I said, I'm gonna keep this particular screen handy just to summarize everything in this chapter over here. So what we have here again is all the formulas that we've looked at so far. Now, to throw in one additional thing over here, okay, what we have now is a second formula to calculate slope. Okay, and you're probably wondering, well, what is that second formula? Well, it was the last one that we did here. So I actually have it hiding down here. Okay, so you're probably wondering now, we have two formulas for slope. How do we know which one to use for what type of scenarios? All right, so for rise over run over here, I'm just gonna make it give me myself more space over here. Okay, we use rise over run for graphs. All right, in general. I should learn how to spell that. All right, so anytime you see a graph, okay, especially if the scale of the graph is going up by one for every box, okay, it's wise to use this. All right, now question is, when do we use this the one on the bottom over here? Okay, this is for all types of questions. Okay, specifically, anytime you see anytime you see graphs with big numbers, okay, or anything where the numbers are not going up by 1, okay, this is the formula to use. Okay, so right now you can see, again, when you're looking at the calculation of slope, you now have 2 options to deal with depending on what type of questions given to you. Now you're going to see ultimately, okay, not just in this chapter, but also for the remainder of the next chapter, that the fancy formula, this is the one you're going to be using more often than rise over run. Like I said, rise over run is the most basic way to calculate slope when you're given a graph, and it is the easiest one as long as the numbers are going up by 1. Okay, but ultimately when you're looking at the calculation of slope, okay, get used to using this fancy formula that I introduced you to today. All right, and that's about it for today. Again, Mr. Callan signing off, and I'll see you in the next lesson.